Hello everyone, welcome to you in this video lecture on displacement analysis. This is lecture number 5 under the subject Theory of Mechanisms and Machines. This lecture is specially designed for the GATE aspirants of mechanical engineering and the students of mechanical engineering having 4-year semester course will also be benefited by this lecture. The content of these lectures are as follows: kinematic analysis and synthesis. We will use graphical method, displacement analysis of slider crank mechanism, displacement analysis of quick return mechanism, introduction to analytical method, and at the end we will solve gate problems. So let us start. The subject kinematics is involved in two activities. One is analysis and another one is synthesis. What is kinematic analysis? Kinematic analysis is performed to determine the displacement, velocity and acceleration of the elements of a mechanism when the dimensions and input motion are known. So in kinematic analysis, the dimensions of all links of a mechanism and the input motions are known. We have to determine the displacement, velocity and acceleration of the mechanism. Whereas synthesis is completely opposite to kinematic analysis. Kinematic synthesis deals with the determination of the dimensions of mechanism to satisfy the required motion. That means the required motion is known to us. We have to select proper dimension of links and other elements. So synthesis is completely opposite to kinematic analysis. Both the synthesis and analysis can be done in two ways. One of the process is graphical method, another one is analytical method. So both analysis and synthesis can be done in two ways. One is graphical method and second one is analytical method. Let us start graphical method. So what are the steps in graphical method? In step 1, we have to draw the kinematic diagram of the mechanism to a suitable scale. So the first step is to draw the kinematic diagram of the mechanism to a suitable scale. The second step, the desired unknown quantities that are displacement, velocity and acceleration are determined through suitable geometrical constructions. So after that we will do some suitable geometrical construction and then calculations. So these are two steps on graphical method of kinematic analysis. Here we will do displacement analysis first by graphical method, and this lecture is involved in displacement analysis only. So we start with graphical method. For an example, we have chosen an offset slider crank mechanism. So first we will do displacement analysis of an offset slider crank mechanism. This is the animation of a offset slider crank mechanism. So this is an offset slider crank mechanism where this is the crank, this is connecting rod and sliding one is the slider. Slider is sliding, the smaller one is crank and this is the connecting rod. So this is an animation of offset slider crank mechanism. So first step is to draw the kinematic diagram of the mechanism to a suitable scale. So we have drawn it into a suitable scale. So in offset slider crank mechanism, the center of crank O2 has an offset with the axis of the slider. So that offset amount E is known. The length of the crank is R, that is link number 2. Length of crank is R. Length of connecting rod AB is L, that is link number noted by link number 3, and this is our piston. So we have drawn it into a suitable scale. Next step is to construct suitable geometrical features. So let us draw this. I am explaining to you. If this point is A, when crank rotates, the point A generates a circle. So this circle is trace point of point A. So this dotted circle is the circle generated by point A. Now our objective is to find what is the stroke of this mechanism and what is the quick return mechanism. So to find what is stroke is the displacement length, total displacement of the slider. So that is the distance between extreme right position and extreme left position of the slider. So how to find the extreme right position of the slider? So what will be the distance? Let us take O2 as a reference point. So at extreme right position of the slider, what will be the distance of the slider center from O2? That is nothing but R plus L. So when the crank and connecting rod will be collinear and one after another, then the slider will reach the extreme right position. So what we will do? We will take radius R equal to L plus R. With this radius, we will draw an arc with center O2, and that cuts the axis of the slider at point BR. So VR is the extreme rightmost position of the slider. So this is the extreme rightmost position of the slider. Now what will be the extreme leftmost position of the slider? The minimum distance of point B from O2 is L minus R. If the length of the connecting rod is L and length of the crank is R, so minimum distance can be obtained when this crank and connecting rod are collinear and one overlapped on another. So at that position, the distance from center O2, crank center O2 will be L minus R. So similarly, we'll draw another arc with radius L minus R at center O2, and that cuts the axis of the slider at point BL. So this is the leftmost position of the slider, and at this instant the crank is overlapped on the connecting rod. O2 AL is the position of crank and AL BL is the orientation of the connecting rod. The slider cannot move beyond this. So this slider cannot be moved beyond this position from the left. So these two are extreme right position and extreme left position. So distance between BL and BR is the stroke. So our stroke is BL BR. Now we have to find out what is the quick return ratio. Say the crank is rotating with a uniform speed in counterclockwise direction. So let us start with this position when crank position is O2AR and connecting rod is AR-BR. So let's crank has been started rotating from this position. So this crank will rotate along. The crank will rotate in counterclockwise direction. It will come to O2AL when when the corresponding movement of the slider is BR to BL. So this is my forward movement. So in forward movement, the slider moves from BR to BL and crank rotates from O to AR in counterclockwise direction and comes to O to AL. So theta F is the angular distance traveled by the crank in counterclockwise direction. So theta F is angle traveled by the crank during forward motion. So I am repeating once again. In forward motion, crank starts rotating from position O to AR in counterclockwise direction and it comes to O to AL, and the rotation of the crank is denoted by theta F, and corresponding movement of the slider is from BR to BL in left hand direction. Now from O to AL, crank maintains its rotation with uniform speed and comes to O to AR, and in this corresponding rotation of the crank, the slider moves from BL to BR, that is the return stroke. So here we will see theta F, that is movement of crank during forward stroke, is greater than theta R. Theta R is angular movement of the crank during return stroke. So forward stroke time is greater than return stroke time. So we have a quick return ratio. So what will be the quick return ratio? The quick return ratio is time during forward stroke divided by time during return stroke. So what is time during forward stroke? The crank moves by an angle theta f. So the time taken by the crank is theta f by omega. If omega is the speed of the crank, and time during return stroke will be theta r by omega. So that is nothing but theta f by theta r. And if this angle BL O to AR is theta, then theta f is 180 plus theta and theta r is 180 minus theta. This theta can be determined very easily because E is known, the distance of horizontal line from O2 and the axis of the slider is known. So E is known and O2BR is L plus R. So angle between BR, O2 and the horizontal line can be determined. Similarly, the angle between BL, O2 and horizontal line can be determined. So theta will be angle between BL, O2 and horizontal line minus angle between BR, O2 and horizontal line. So theta can be determined from this geometrical construction and we will find the quick return ratio. So this is the end of displacement analysis of an offset slider crank mechanism. Now let us come to the displacement analysis of a quick return mechanism. All of we know a quick return mechanism is used in shaping machine. So where return stroke is faster than the forward stroke. Because in return stroke there is no cutting, so if we return faster, then the production rate will be increased. So to improve the production rate, quick return ratio is used in shaping machine. This is the kinematic diagram of a quick return mechanism. The link 1 is the fixed link, that is O4O2. O2A is the crank denoted by link 2. 3 is the slider. 4, that is O4B, is link number 4, that is the slotted arm, and BC is link number 4, and 6 is the slider on which tool is attached. So this is the kinematic diagram of a quick return mechanism. Now let us see an animation of the same. Here this is the fixed link. Crank 2 is rotating with uniform speed in counterclockwise direction. This is the slider which is sliding through the slot made on link number 4. So this is link number 4 on which the slot is made. This is link number 5, and the slider which is moving like this, that is link number 6. And on this slider on link number 6 the tool is attached. Now say forward stroke is from right to left position, this is slower, and return is from left to right, that is faster. See here, this is the forward stroke, now return stroke, it is faster. So return speed is more than the forward stroke, or return time is lesser than the forward time. Now let us move to the second step, that is we have to draw suitable geometrical construction. Now our objective is to find out the stroke and the quick return ratio. To find out the stroke, we have to determine what is the extreme right and left position of the slider C or the link number C. What is the extreme right position and what is the extreme left position? How to determine? The crank is rotating with a uniform speed. So when the crank is rotating, this point A will generate a circle about center O2. So this dotted circle is the trace point of point A. This is the circle generated by point A. Now what will be the extreme right position of link number 4, that is the slotted R. So the link 4 at extreme right position will be tangent to this circle. So at extreme right position, link 4 will make a tangent with this circle generated by point A. Now we will draw a tangent from O4 to the circle, to this circle, and with the length of link number 4. So the extreme right position of slotted link has been represented by O4 BR. BR represents right, R subscripts R denotes rightmost position. So O4 BR is the extreme right position of this slotted arm link number 4. And similarly we will draw a tangent in left hand side with the length of link number 4, that is O4 BL. So this is the extreme left position of the slotted arm or link number 4. Now at this position of, at this instant when it is at extreme right, the crank will be at O2 AR. The crank will be at O2 AR, and for extreme left position the crank will be at O2 AL. Now we have to determine the position of C corresponding to this extreme right position. What we will do? At center BR we will draw a arc with radius equal to link number 5 that will cut the axis of the slider 6 at CR, and CR is the corresponding position of the slider. So CR is the extreme right position of the slider. What we have done? At center BR we will draw an arc with radius equal to link number 5, equal to length of link number 5, that will cut the axis of this slider at CR. So CR is the extreme rightmost position of this slider. Similarly from BL we will draw an arc with radius equal length of link number 5 that will cut at CL, and CL is the extreme left position of the slider. Now CL CR is the stroke. Now my stroke is CL CR. Now when the slider at CR, the corresponding position of crank is O2 AR. Now let us start from here. The slider is at CR, oscillating link as O4 VR, and crank is at O2 AR. Now crank start rotating in counterclockwise direction. and it reaches to position O2AL, and the corresponding movement of the slider is CR to CL. So this is my forward stroke, and angle traveled by the crank during forward stroke is theta f. So this is angle theta f, and corresponding movement of the slider or tool holder is CR to CL. So forward stroke is from right to left, and from O to AL, crank starts rotating counterclockwise direction and reaches to O to AR. In the same time, the corresponding movement of this tool holder or link number 6 is CL to CR. So this is the return stroke. So forward stroke is right to left and return stroke is left to right, and corresponding movement of the crank is shown here. One is theta f and return angle is theta r. So theta r is less than theta f here, so we'll get a quick return ratio which is more than 1, and at the corresponding position angle O2 AR BR is 90 degree because this is tangent to this circle, and angle O2 AL BL is 90 degree. Now what is my stroke? I have already described that CL CR is the stroke, and the quick return ratio is time during forward stroke by time during return stroke. So that is theta f by omega divided by theta r by omega, that is theta f by theta r. So how to find theta r? Theta r can be easily determined because this angle O4 O2 AR is theta r by 2. So cos theta r by 2 is equal to O2 AR, that is crank length, divided by O4 O2, that is the length of fixed link. So theta r can be determined easily, that is cos theta r by 2. So if theta r is determined, then theta f is 360 degree minus theta r. Now if we want to reduce the stroke length, what we have to do? We have to reduce the crank length. If we reduce the crank length, then the radius of this circle will be reduced, and these two links BL and BR will come towards the center O2, and corresponding movement of CL and CR, they will come to at the center, and the stroke will be reduced. So the stroke can be reduced by reducing the radius of the crank. But there is a problem. If we reduce the crank length to reduce the stroke, what will happen to quick return ratio? So cos theta r by 2 is equal to r is the crank radius divided by this fixed link. So this fixed link is fixed. So if r reduced, then value of cos theta r by 2 reduced. So reduction in cos value means angle is increased. So theta r by 2 will increase, and theta r by 2 will increase means the quick return ratio decreased. So if we want to reduce the stroke length by reducing the radius of the crank, then our quick return ratio will be reduced, which is not desirable, because if quick return ratio is reduced, then production rate will lose production rate. So if stroke length reduced, then quick return ratio also be reduced. So quick return ratio has a dependent quick return ratio on the crank length. In quick return mechanism, we have seen that the quick return ratio is a function of crank radius. If we reduce the crank radius, then the stroke will reduce as well as quick return ratio also reduced. But reduction in quick return ratio implies that the production rate will also reduced. So this is not a desirable phenomenon. One solution to get quick return ratio independent with crank radius is given by this mechanism, which is called Whitworth quick return mechanism. So an independent quick return ratio can be generated in Whitworth quick return mechanism. This is also a 6-link mechanism. O2A is the crank. This slider is link number 3. This is link number 4. This is link number 4. BC is link number 5 and 6 is the slider. So this much information is sufficient for your gate examination. But if somebody wants to find what is the quick return ratio of this mechanism, I am giving a hint. What you have to do, you have to draw a circle with radius O2A, that is the crank radius, from point at center point O2. So you draw the circle. That circle will intersect with this axis of slider 6 at 2 points. That 2 points will be the points at which this slider 6 will be at extreme right position and extreme left position. So corresponding position of A will be 2 intersection point with this circle generated by point A and axis of slider 6. Now let me introduce with the new method or the second method, that is analytical method. Here we will do displacement analysis by analytical method. So the first question is that when we will use analytical method? The analytical method is preferred over graphical method where higher accuracy is required. So analytical method provides higher accuracy. Why accuracy is poor in graphical method? Because there are some constructions. So in the construction there may be some error in the drawing. So that can be avoided in analytical method. So we will get higher accuracy in analytical method. And second one is, if a large number of link is present, then graphical method becomes complicated. So if in a mechanism contains a large number of links, the graphical method will becomes complicated. So 2 points is there when we will use analytical method. Number 1, if we want higher accuracy, and second one, if there is a large number of link present in the mechanism. So what are the steps now? What are the steps to follow in analytical method? All of we know a mechanism is a closed kinematic chain. So in the mechanism we have to identify a closed kinematic loop. So first step is to identify a closed kinematic loop. The second step is to generate loop closure vector equation, and we'll convert that equation into two scalar equation to solve unknowns. So we will get two scalar equation. So from these two equation we can solve two unknowns. So let us take an example, and here we will take an example of a 4-wall linkage. So O2AB04 is an 4-wall linkage on which we are going to apply analytical method to find out its displacement, that is position of all links. Now we have chosen a coordinate system, that is xy. Xy are two perpendicular axes where x-axis is along the link 1, that is O2O4. So x-axis is such chosen that x-axis is along link 1. So in analysis, the length of all links, that is L1, L2, L3 and L4 lengths are known. And the input angle, that is if O2A is link number 2 and it is the crank, then the input angle, that is crank angle theta 2, is also known. So how many unknowns are there? Only theta 3 and theta 4. How to find them? So first step is to identify a closed kinematic chain. So we have noted these links as a vectors, and these vectors are formed a closed kinematic loop. So this is the closed kinematic. L1 plus L4 plus L3 minus L2 is equal to 0. So the resultant of a closed vector is 0. So the vector equation will be what? L1 minus L2, because plus L4 plus L3. So L1 minus L2 plus L3 plus L4 is equal to 0. So this is the loop closure vector equation. Now if we take components of all vectors along two mutually perpendicular axes, that is x-axis and y-axis, the resultant of components along two direction will also be 0, because this is a closed loop vector. So what will be the equation? The equation along x direction or x-axis will be L1, because L1 is along x, minus L2 cos theta 2 plus L3 cos theta 3 plus L4 cos theta 4 is equal to 0. So this is the first equation along x direction. Now the second equation will be the component, all components along y direction will be 0. So minus L2 sin theta 2. So minus L2 sin theta 2 plus L3 sin theta 3 plus L4 sin theta 4 is equal to 0. So we get two scalar equation, out of which L1, L2, L3, L4, these are the linked lengths, and in analysis the all linked lengths are known. So these all are knowns, and input angle theta 2 is known also. So only unknown is theta 3 and theta 4. So from these two scalar equation, two unknowns can be solved easily, and we will get the orientation of all links. So this is analytical method we have described here. Now let us start problems of gate examination. So this is problem number 1, which states an offset slider crank mechanism is shown in the figure. So this figure shows an offset slider crank mechanism. The quick return ratio is considered to be greater than 1. The value of quick return ratio is to be determined. So how to solve this? So we have already do this analysis in graphical method. So first of all we have to determine two extreme positions of the slider, which are noted by A and B here. So these two are the extreme position of the slider. The eccentricity value is 10 mm, the crank length is 20 mm, and length of connecting rod is 40 mm. So how to find or how to locate point A, that is the extreme right position? From point O, that is the center of the crank, we will draw an arc of radius how much? 20 plus 40, that is 60. So OA is 60. So A has been located. Now how to locate B? What is the minimum distance from O2? From O2 to the center of this slider, that is 40 minus 20 is 20. So B lies on the center, which is generating by this point on the crank. So this is the point this is the circle generated by the point on this point on the crank. So this is the leftmost position and this is the rightmost position. This is the angle corresponding to forward stroke and this is the angle corresponding to return stroke, as we have done in our previous analysis. So we have to find out angle BOC. If BOC is theta, then quick return ratio will be 180 plus theta by 180 minus theta. So from the geometry we can obtain angle BOC. How much is angle BOC? That is sine inverse 10 by 20. OB is 20, and from distance from B to this horizontal line from center O is 10. So this angle is BO, and this horizontal angle between BO and this horizontal line is sin inverse 10 by 20. Similarly, this angle AO and angle between the horizontal line is sin inverse 10 by, this is 20, this is 40, so 60, sin inverse 10 by 60. So angle BOC is sin inverse 10 by 20 minus sin inverse 10 by 60, and this becomes 20 degree. So BOC is 20 degree. Now what will be quick return ratio? 180 degree plus 20 degree divided by 180 degree minus 20 degree. So angle COD becomes how much? 180 minus this angle 20, 160, and quick return ratio is 200 degree by 160 degree, that is 1.25. So quick return ratio of this offset slider crank mechanism is 1.25. Now let us come to the next problem, that is problem number 2. A quick return mechanism is shown in the figure. The crank, this is the crank OS, is driven at 2 revolutions per second in counterclockwise direction. The fixed length is 500 mm. The quick return ratio is 2:1, then the length of the crank in millimeter. That is a very easy problem. So this I have explained to you before. This is the two extreme positions of the slider, and when the slider or tool holder is at extreme right position, the oscillating link, that is link PQ, will make a tangent to the circle generated by point S. So PQR is perpendicular to OSR, and angle POS is theta R by 2. So right now we know OP, and theta R by 2 can be determined from the quick return ratio. So if quick return ratio is 2:1, then theta R by theta F is 2 by 1, and we know that theta R by theta F is 360 degree. So equating these two equations, we can find the value of theta R. Theta R will be 120 and theta F will be 240. Now what is cos theta R by 2? So theta R by 2 is POSR. Theta R by 2 is an angle POSR. So cos theta R by 2 is OSR by OP. OSR by OP. OP is 500. OP is 500 and theta R by 2 is 180 by 2, that is cos 60 degree. So cos 60 is half. So OSR is nothing but the link length OS, because subscript R is to denote the rightmost position. So OSR is equal to crank length OS is equal to 250 mm. So we have solved this problem. So option A is correct, and we have completed our lecture here. Thank you for watching this. I wish you best of luck in your GATE examination. Jai Hind.